Every student of A-level maths will be expected to familiarize themselves with a large data set. For Edexcel, that large data set is the same year on year, and it involves data collected about the weather in various places. The first thing you need to know about this is that it isn't some kind of extra page in your textbook or even a pre-release document with a table of numbers. It is a spreadsheet that you're expected to download and manipulate in the same way that anybody who's working with data does these days. So start by searching the internet for large dataset Edexcel, and it should come up right at the top. Dataset Pearson qualifications. This is the one you're looking for. There'll be plenty of other links below that you can find versions of the same thing. If you download that, you should be able to open that in any spreadsheet. So even if you don't have Microsoft Excel, you can still open it and work with it. You can work with it in Google Sheets online if you don't have something installed on your machine. We can enable editing. that will allow us to mess about with this and play with the numbers. And the first thing you should do is read through the information sheet on the front. There's lots of information here, so start by just skimming across. You'll get a sense of what places are involved. So there's a number of places in the UK, and then there's a handful of more international places where weather data has been collected as well. For each of the places, data has been collected on some of the most common things you might be interested in: temperature, rainfall, sunshine, humidity, wind speed, cloud cover, visibility, etc. Now, depending on the data that's been collected, it may be in various different forms. So the next thing you want to do is click across and have a look at some of these tables. They should look all pretty similar. In fact, the first few will have exactly the same columns along the top and similar looking data underneath. As you get further along, you'll find that the names change slightly. So Leeming, May to October 1987, and now we're in Leeming, May to October 2015. So we've got a 6-month period of a year way back when, 1987, and another one somewhat more recently, which gives potentially the opportunity for comparisons within the same time of year and the same location, but a sufficient number of years distant that perhaps any slightly more long-term trends would potentially be recognizable. If we go a little bit further along, you'll find suddenly we get Beijing. Again, May to October 1987, so comparable in terms of the time that the data was collected, and we have May to October 2015. But the thing you'll notice about this table is that there's less data that's been collected. There are fewer fields in here, fewer columns to look at. We've got the daily mean air temperature, rainfall, daily mean pressure, daily mean wind speed, and daily mean wind speed, both at conversion. We'll look into each of those in a bit more detail later on. There's also Jacksonville, which is in the States, and Perth in Australia. So we have slightly more limited information for the more international places and more detail for the UK locations. But the UK still record things like the daily mean temperature, the daily total rainfall, the pressure is given for both daily mean pressure, etc. So no matter where you are, there are certain things that are measured for all locations, and there are some things that are only measured in the UK. The next thing you might want to do is start playing with the data. If you go down a little bit, you'll notice, well, we've got data for every single day for a 6-month period. So hold down Control and press the down arrow. It'll jump you to the very bottom of the column, and you can see we have nearly 190 different days, each one with maybe a dozen or so pieces of data recorded. If you go up to the top, you can see just how many different things have been recorded for each day. At the bottom here it says count 14. So we know there are 14 columns there. There are 14 different pieces of data that have been collected for each day. But in order to make sense of these, 3.8, TR, 9.1, 8, we need to know what those things are measured, how they're measured, and what units they're measured in, how the data has been collected. That is where you want to go back to the information slide and look in more detail. Pick one thing to start with and focus on that so you don't get completely distracted and confused, overwhelmed by the number of different things to look at. Maybe focus on temperature to start with. It's something that we all have a fairly intuitive sense of, and you might already have some idea of whether you would expect Beijing to be hotter or colder than Perth in the middle of June, for instance. The daily mean temperature is recorded by thermometers in a louvered screen 1.25 meters above short grass, except at some weather centers and climate data logger stations where observations are made from a non-standard rooftop exposure. Values are noted in degrees and tenths degrees Celsius, and values below 0 degrees C are preceded by a minus sign. A reading which is not available is listed as NA. The daily mean air temperature, 9 o'clock to 9 o'clock, is the average of the hourly temperature readings during this period. In other words, they will take a temperature reading every hour on the hour for 24 hours and then take a mean average of those 24 readings. The first thing I would notice from this is that means we're including the nighttime temperatures as well as the daytime temperatures. It's a 24-hour average. And that means that if you're looking at one of the temperatures in here, if we go to Hearn 1987, for instance, and we come down to June or July, we can see the kind of temperatures we're dealing with. There was a day there with 23.2. That might not seem particularly high for a summer's day, but if you consider the fact that we're dealing with the average of the daily temperature and the nightly temperature, we can start to appreciate just how warm that might have been. We might be dealing with a temperature of 10 degrees in the night, but 30 or more degrees during the daytime. If the temperature drops particularly low, then that gives you some indication that perhaps it was particularly cold in the day as well as the night. So that's worth being aware of. Now, there's too much data here to scroll down and get a feel for every single thing that's being measured. What we can do is summarize them. This is what spreadsheets are the most useful for. When you first come across a spreadsheet, you might be naively using it in the same way that you would use a table of numbers on a sheet of paper. You might be scrolling up to the top and the bottom and circling things that look interesting, coloring in different things perhaps. But the power of a spreadsheet is in the calculations that it enables you to do, summarizing the data so that you can pull out trends and patterns that you wouldn't otherwise see. The first thing that I want to show you is probably one of the simplest, the first functions that you might come across. We could look at something like the average. Excel allows you to compute all sorts of things, and the simplest way to find out how to do it is to start typing in the thing you want to calculate. If you want the sum, you put equals and then sum, open bracket. And then Excel will start telling you a little bit about it. If you want more information, if you hover over the word that pops up underneath, you can click on that and it'll give you some additional help on that particular function. You'll soon find this pretty intuitive way of learning new things. If you decide you want to calculate the median of a set of data, there is a way of doing that, and you can read up about it in here. This, for instance, tells you that you can put a range of values in. A1 colon A20 refers to all of the values in cells from A1 all the way down to cell A20. If you select all of those cells, then Excel will be looking at all of those cells. Of course, they're not the cells we want. We want to select all the cells from B7 all the way down to something like B190. Now you can type it in, B7 colon B190, but that assumes that you already know where your data goes down to. I'm using Control and the arrow keys to jump to the bottom of a table, and it does happen to be B190. We can also use the Shift key to quickly and easily select things. So if I type in average, open bracket, and then I'm just using the arrows to move to a sensible starting point. If I hold down Shift, and now I use the right arrow or the left arrow, or I use the down arrow or the up arrow, I can start selecting a range of cells from that starting point. Now, if I want to go all the way down to the bottom, I can hold the down arrow, but it'll take a little while. If, on the other hand, I hold down Control as well as Shift and press the down arrow, I jump straight to the bottom of the range, just like Control and down arrow, but because I'm holding down Shift, it selects all of the things that I'm going past as well. Then we close the bracket, and you can see that formula in the top of the screen as well, even though the cell we're interested in is not currently visible. And when we press Enter, it gets calculated for us, 14.6. So that gives you a good sense of the average temperature for the entire 6-month period. It doesn't give you the complete picture by any means. Summary statistics always miss out information, but it does tell you something useful. Not only that, we can copy this, Control C, and then move to a different cell and paste, Control V, and you'll find that this formula, if we press F2, you can jump into it, or you can double click on the cell. This formula refers to the average of cells C7 to C190. In other words, the formula has moved across and it has intelligently as predicted what we're going to want to do. If I copy and paste, it assumes that I want to find the average for the column that I'm now above. So the average pressure, 1014.8, the average daily mean wind direction, 218.8, and so on. It's worth looking at the columns where we're getting an error. Divide by 0, this is an error you get if you try to divide by 0. And the reason there's division by 0 going on behind the scenes is that a mean average adds up all the values and divides by the total number of values. The way Excel deals with non-numerical data when you ask it to average things is by ignoring it. So for instance, if I take the average of these four, 250, 290, west, southwest, and west, northwest, the result comes out as 270. In other words, it's the average of the numerical values. It's added up all the numerical values and divided by the number of numerical values. That's how that will work. And that means that if you've got some values missing, for instance, in the daily total rainfall, there is TR, stands for trace. If we read the information, it'll tell you a little bit about that. But that means essentially there is a small amount of rainfall, so not 0, but too small to register as one of the low values that you might otherwise see somewhere else. Now that trace will be ignored by this average. And one thing you might want to think about is the effect that has if trace actually represents a small but non-zero quantity. What will the impact be if we take an average, a naive average like this, where Excel ignores anything that is words rather than numbers? And of course, the other thing is, if we don't have any numerical data, like with this column, where even when there is data, it's a qualitative description, light, moderate, something like that. In that case, you're not going to get a sensible average. We'll get divide by 0 because there are no numerical values. But that's fine, not a problem there. The next thing you can do, if you highlight all of these, we can move to an entirely different sheet. And if we are careful to pick the same starting cell, we can paste all of those formulae. And suddenly you've got an average for every single data field for the entire set of nearly 190 pieces of data. We've got Heathrow and we've got Herne. So we could compare them. For instance, Herne has a daily mean temperature of 13.7, daily total rainfall average of 2.4, whereas in Heathrow we're getting a daily mean temperature of 14.6, a little bit higher, and daily total rainfall average coming out as 3.1, which is a little bit higher again. So warmer and wetter in Heathrow on average than in Herne during those 6 months. There's lots more you can do with this. You can, for instance, instead of calculating the mean average using the word average, you could calculate the standard deviation. STDev is the way you find standard deviation. There's a couple of variations you can use as well, but they will give similar-ish numbers, so it's not a particularly important distinction right now. If we calculate the standard deviation, that gives us a measure of how much variation there is within the data. In some countries, you might find that the temperature is high and consistently high. In other countries, you might find the temperature is high but inconsistently so. Some days it's very, very high and some days it's very, very low. You might have extremes of hot and cold in certain countries, and yet in other countries where we have a more temperate climate, you wouldn't expect the temperature to get much above, let's say, 25 degrees for an average daily temperature, or much below 10 degrees for an average daily temperature. So it's another useful measure to look into, and there's plenty more of those useful measures. However, there are a lot of different sheets in here, and if you try to go through and calculate every single potential useful statistic for every single piece of data, you'll be overwhelmed. So what I'd suggest is that you do a combination of getting some big picture sense of what's happening and some deep drilling into particular things that you're curious about. The best way to approach this is with questions. If you have a question in mind, like, does it rain more in Australia during the summer than it does in America? Well, we can pick out the data we have, which is Perth and Jacksonville, and compare them and see if we can answer that question. Is there a significant difference? Your question might be, related to the connection between two things. Some of these things have a close correlation. It might be that you want to draw yourself a scatter diagram, maybe the mean total cloud cover in octas and the mean visibility. Perhaps there's a connection between those. If you look at the information on the original sheet, it'll tell you that cloud cover is given as a fraction. So it'll be something between 0/8 and 8/8. That's what octas represents. So the visible sky is either completely covered in cloud or mostly covered in cloud or some mixture of the two. Daily mean visibility is related to how far you can see, measured in dm. You'll have to look that up, I believe, decameters. So it's an awkward one because it's not meters and it's also not kilometers. It's something a bit weird, but you can look up the conversion for that and commit it to memory, because these are the kind of details that demonstrate in the exam that you have a familiarity with the data set, and also they allow you to get a sense of what the numbers are really telling you. Now, if you want to see a graph, you'll need to go to Insert in Excel. There are similar things in other spreadsheet programs. And then if you find a scatter graph picture, click on it, choose something sensible looking, and there's your data. We can look at it in more detail. You can see the interesting clumping along these lines. That happens because the daily mean total cloud cover is discrete data. They're essentially rounding to the nearest eighth of the sky. It's a visual measurement of what fraction of the sky is covered in cloud, but it's going to be rounded. So it's either going to be 4/8 or it's going to be 5/8, but they're never going to record a 4.7 or a 4.2. If you think there's a trend in there, then you right click on one of the data points and you can click Add Trendline, and it'll give you a sense of what kind of trend there might be. And if you look at it and think, oh, I thought it would be a positive correlation, but it looks like it's negative. Well, it might be that there's not enough correlation for you to say anything very strong about it at all. To me, it looks like that line is fairly arbitrary. I wouldn't be confident using it to predict anything. We can display the equation of the line if it's worthwhile, but the r² value you'll learn about as you go through the course, the r² value represents something to do with the correlation, the strength of the correlation and the direction of the correlation. There are also Excel formulae that you can use to generate all of these numbers if you don't want to create a graph for every single pair of data fields that you're interested in comparing. But sometimes there'll be a strong connection, sometimes there might be a weak connection, and sometimes you just have to say, look, there's no real connection here at all. We thought there might be, but it doesn't appear to be related. How much you can see on a clear day, whether there's clouds in the sky or not, maybe there's not that much connection between them. Now, the last thing I want to show you is a tool that I've created that you might find useful for doing some big picture investigations. This makes it a little bit easier for you to ask the questions you might want to ask. Over here, we've got the key statistics calculator. You can pick a year that you're interested in. You can choose a location that you want to investigate. You can decide which particular thing you want to find out about. So perhaps we look at rainfall in Beijing in 1987. And I'll start by calculating the mean. Seems sensible. Now the rainfall is measured in millimeters, so that's shown here. And it shows me the mean. Traditionally, we use the Greek letter mu to represent the mean, and the mean was 3.04. Well, that may not tell you very much, but if you wanted to see something comparable, we could ask about Heathrow. Okay, 3.07, so similar. And maybe you ask about Perth, and we find 3.97. So you get a sense of what that number means compared to other places. The other thing you can do is stick with Beijing, stick with rainfall, but maybe find out the standard deviation, how much variation you would expect to see. In this case, 9.09. And if we wanted the minimum, we could pull that out as well. So 0 will be a minimum. That kind of makes sense for rainfall. You're not going to get anything negative. That makes the standard deviation of 9.09 even more surprising if you think about it, because the standard deviation, roughly speaking, gives you a sense of, on average, how far the data is from the average. So you might say, well, it's going to be 3 millimeters, give or take about 9 millimeters. But clearly it can't be 3 millimeters, take away 9 millimeters. So maybe then you say, I'm going to look in more detail what on earth is going on in Beijing in 1987 with rainfall. And this is our data. If you want to see the summaries of it, it's helpful to use the calculator at the beginning. But if you want to see a more visual form, we go to Insert Graph, and maybe this time we go with some sort of histogram. And we can see that by and large, we're getting numbers that are quite low. So the average was 3 point something. We're getting almost every day, we're getting somewhere between 0 and 5.6 millimeters of rainfall. But there are a few days where we get enormous quantities of rainfall. So we get what's called a long tail. There are some days that are recorded in here as getting 60 something millimeters of rainfall a day. And that is what is skewing the standard deviation so far. If you want to do a similar thing for different places, if we look at, for instance, Jacksonville, we can see what rainfall is like there. We find still quite a big standard deviation, but a slightly smaller average overall. If we look at Heathrow, we find a smaller standard deviation again. So apparently there's less variation in most places than in Beijing, but there's still enough variation that we can tell there is going to be a skewed distribution with any of these places. As you can see, we can look up all sorts of things. If you want to calculate the interquartile range, then you can do that. If you want to look at maximums and minimums, you can do that as well. Give you a better sense of exactly what this range is. So there were some days in Heathrow where we got 53.1 millimeters of rain compared to the average of 3. Now, I've also put in here a summary for each of the types of data. There is a brief summary, which is taken from the information sheet here, but put into a slightly more convenient form, I think. Decameters, for instance, 1 decameter is 10 meters, which is 0.01 kilometers, and it's the maximum distance visible. If you want more detail on that, read the information sheet. If you just want a brief summary to remind you what it represents, read this. In previous papers, they've asked questions like, convert 12 knots into miles per hour, and therefore compare the wind speed in Camborne with the wind speed in Heathrow, given that the average in Heathrow was 15 miles an hour and the average in Camborne was 13 knots, whatever it might be. They won't expect you to know all the data, but they will expect you to have familiarized yourself with the type of data that's available and have some sense of where the anomalies might be, where there's a particularly surprising high result somewhere, for instance. If we look down here, you can see a convenient way of generating scatter graphs. All you need to do is choose your X and your Y. So in this case, I'm plotting pressure against temperature during the same 6 months in Beijing in 2015. We can see quite a strong correlation between the two, according to that. There are measures for correlation. So we can see the correlation measure here, negative 0.7332. That means there's quite a strong negative correlation. The reason for that could be all sorts. It may be that there is a causal connection. If the pressure changes, that impacts the temperature potentially. It might be that if the temperature changes, that impacts the pressure. And it might be that some third factor is driving both of those two things. It's also possible that the two things are not connected and that any correlation you see is fluke or coincidence. We've got quite a large number of data points for these, so you're likely to get a clearer sense of whether it's coincidental or a real connection. The other thing you might be interested in is a time series graph. This shows you how things change over time. Because we've got data for every single day, we can look, for instance, at how the temperature in Beijing has changed during the months. And if you wanted to look at, say, temperature in Perth and compare it to the temperature in Beijing, we would see something interesting here. Temperature in Beijing it has spikes, it goes up and down, but in general it gets higher towards the end of July, beginning of August, and then lower again. Whereas Perth seems to be lower in the middle and then higher at the other side. You might want to ask yourself, what is it about the location of Perth compared to Beijing and compared to places like Heathrow, for instance, that might give some clue as to why Perth in the middle of Australia looks colder than Heathrow in the middle of quote-unquote summer. Think about northern hemisphere, southern hemisphere, that kind of thing. You might at this point be feeling a bit daunted by the geography you're expected to know about. It's not necessary for you to be a geographer to make use of this data set. There's a few things where you want to use some common sense. So you might want to think the gust direction, for instance, is the direction in which the wind is blowing when it's blowing its fastest. that's likely to be closely related to the direction that the wind is blowing on average during the day. So there are connections there that are more or less common sense when you spend a bit of time thinking about them. You might look at humidity, which is a measure of how much moisture is in the air, and then perhaps visibility. Maybe those two are connected because visibility is how far you can see, and generally speaking, that's going to be affected by how much moisture is in the air, whether it's a really foggy day, for instance. I've included the formulae that you're probably most likely to want to use, but this calculator will allow you to bypass some of the nitty-gritty brute force that you might need to investigate things on your own. I would still encourage you to use these to get a sense of how they work, but hopefully this calculator will mean you don't have to do the same thing repetitively over and over again to be able to investigate things that you might have seen. The last thing I want to talk about is a few things to look for in the large data set. So there's a large data set treasure hunt that you should be able to download and look through. Are there any data points that are particularly surprising that just don't fit? Are there any days when the temperature has been recorded as 115 degrees centigrade, where coffee is going to boil before you put it in the kettle and things like this? Are there perhaps some bearings that should be between 0 and 360 degrees that are not between 0 and 360 degrees? Have a look at the graph connecting the direction the wind was blowing when it was blowing at its hardest and the average direction during the day. You might expect a correlation. There's something interesting about the way we record direction of the wind that makes the correlation a little bit suspect. So you want to look at what the graph looks like and figure out what's going on with that. It's quite an interesting one. You can use conditional formatting to get a sense of the overall temperature trends. So this I briefly want to demonstrate. Conditional formatting is not as fancy as it sounds. All you have to do is highlight a particular set of cells, and in the main home tab in Excel you can find this box called conditional formatting, and there are lots of built-in options for this. The simplest is probably color scales. If you choose color scales and you pick one of these, then immediately you'll see there is a gradation here. We've got red for the very low values like 0 and 0.1, moving up towards green for high values like 9.6. You can even zoom out and ignore the numbers entirely and get a feel for how much variation there is visually. This is not an unuseful thing to do because it gives you very quickly a sense of how things are changing, where the particularly high points are. If there's a sudden change between high and low, there are places where you might want to investigate a bit more, and perhaps to get some idea of whether it's connected to other things, you investigate something else. Daily mean pressure, for instance, we can look at the same kind of things and see if pressure is somehow related. Are there places where particularly high pressure has caused some similar trend elsewhere, or is that not really what's going on? This is kind of an alternative to drawing a scatter graph and looking for correlation, but it's quite a nice visualization of what you're doing. There are a couple of other things to look up. There's a couple of links here you can go into, read about the hottest day, read about the great storm, and see if you can find evidence within the large data set in the relevant locations for those events that happened. I've also included some summary statistics here because there's quite a lot of work involved in computing all of these. I've got the average, the standard deviation, the minimum and the maximum for the main data types that you might measure for each of the different places in the world. So you can see at a glance, for instance, that the pressure in Beijing is generally a lot lower than the pressure in Perth, which is quite high compared to all the UK values, which are somewhere in the middle. You can look then at how much standard deviation we've got, and for pressure, there's a lot of very high standard deviation in Liming and Lucas, which are further north in the UK compared to the rest. Very low standard deviation in Jacksonville, so we're expecting not much variation there. You can see very high low pressure for Jacksonville and a very low high pressure for Jacksonville, which fits with this idea of a low standard deviation. So there's a lot you can see by looking closely at these tables. You might also want to read this slightly augmented version of the information sheet, because in addition to all the information they've given you, I've got a few extra pieces of information here, some suggestions on how to get started. And then one thing you might want to do when you feel like you've spent a bit of time with this is to go through and look at a single line, see if you can remember what each of these things is calculating. What does the 10.6 represent? What is TR? And what's the relevance of that TR as opposed to a number? What is 1.8? Is that particularly high, particularly low? What are we talking about? So that's a good way to check that you know what you're dealing with, you know what's being measured and what those things mean. I'd encourage you to play around with this large data set for yourself, draw some graphs, see if you can spot any interesting anomalies or errors in the data. Remember, this is real data, so there will be errors. Some of them I've found, some of them I'm sure I have yet to find. Some data is qualitative and some data is quantitative. Some data will need to be cleaned, which is a technical term for parsing the data, for going through it and finding, identifying and updating things or changing things, not messing with the data in order to hide the truth, but actually messing with the data in order to better represent the truth. One nice example of that is this trace, TR, that keeps appearing in rainfall. If we look at the information about rainfall, it tells us daily total rainfall refers to 24-hour periods commencing at 9 o'clock, includes solid precipitation such as snow or hail. A trace, or TR, of rain is an amount less than 0.05 millimeters. A reading which is not available will be shown by NA. All totals are in millimeters. In other words, if they've not got a reading, they'll put NA. If they do have a reading, but it's too small to round up to 0.1 millimeters, then they will record it as trace. However, there is also a 0. So some days there is no rainfall. It's a dry day and it's definitely dry, so we get a 0. On other days, there's a very small amount of rainfall, like here where we get 0.1. And in those cases, whatever the amount of rainfall really was, maybe it was 0.67, maybe it was 0.067 would round up to 0.1, maybe 0.14 would round down to 0.1. But then when we see trace, that's a value somewhere between 0.1 and 0. So it might be sensible to fill in those values with 0.05. Here's where some useful formulae might come in handy. It might be that you use find and replace, Control F. You can look up TR, and every time you find TR, you could replace it with a specific thing like 0.05. And you'll find there's quite a lot of them, so you might want to do a replace all. And then you'll see exactly how many have been adapted. It might be that you keep track of the average before and after and see what happens. It might be that you find other things in here that you need to do adaptations for that are a bit more sophisticated. And there are ways of doing that as well with formulae. For instance, if you want to take this direction and add 360 to it, we can just make ourselves a new column where the values are higher by 360 degrees. It'll give you an error whenever the data is non-numerical, but that's not necessarily a problem for us because usually the formula that we're using will take that into account. So, without further ado, I'm going to sign off and let you have a play around with this for yourselves. If you have questions, make sure you talk to your teachers and you discuss with other classmates. See what you can discover about the large data set and see if you can answer any questions. See if you can come up with questions to ask about the large data set. And if you're not sure how to ask them or not sure what data you need to collect in order to get a response that makes sense to you, then make a note of that, bring it along to your lessons, talk it through with people, and hopefully you'll be able to get pretty good at messing around with real data in a real spreadsheet.